So thank you for being here, and we're going to be talking about we announced last week, and we're giving you the full details today about our custom tensor extensions to run AI and ML workloads. So without further ado, some of you may not know us. We are a European company based in Barcelona. We provide RISC-V IP, which I'll show very briefly in the next slide. And we are really delighted to work with our customers to customize our IP solutions to whatever they need. So we enjoy getting difficult problems from our customers and changing the IP to match whatever the customer needs. So we call ourselves experts in open core surgery, right? Very briefly, because I do want to get to the tensor stuff, we are providing two RISC-V cores. One's called Atrevido, the other one's called Avispado. You have the translations underneath. The Atrevido family is out of order, and you can configure it for 2, 3, or 4 wide. It's a full 64-bit core, and you, the customer, can select AXI or CHI. So you can, if you need a non-coherent system, it's AXI, but if you need coherency, it plugs in directly onto any CHI NOC. And in fact, we've announced recently partnerships with NOC vendors that provide CHI solutions. So easy peasy, right? The Avispado family is in order, also 64-bit, also AXI and CHI, and both of them support the vector extension, which is not the topic of today, but it's important because everything we've done with Tensor is based on the vector unit. So we do need the vector unit here, so it's important that you remember that we have a vector unit, right? The usual slide saying that AI ML is everywhere. I don't need to teach the room about the billions of parameters, trillions of weights, and all that stuff. But what is important is that the vector extension is great, but it is giving you a performance boost over scalar, but it's not enough for the new generation of AI workloads. So people want more. They need a vector unit, and you need a vector unit because you're going to be running the many layers of your network have two parts, right? Matrix multiply, and then something that's not matrix multiply. And that's something, sigmoid, ReLU, you name it, is going to be run on the vector unit. So you want a vector unit, and you want something to run matrix multiply fast. And so our solution has been to add tensor instructions directly on the vector ISA. Of course, these are custom, so these are semi-dynamics. But they're very simple, as you'll see. We made 3 key decisions. First, directly connect to the vector unit, so no new state, literally no new state. Really easy programming. We work hard, or we think we achieved our goal to make it really easy to write a matrix multiply. In fact, I'll be able to show it on the next slide. 3 new instructions, matrix multiply instruction, no surprise, and 2 new flavors. 1 flavor of load, 1 flavor of stored. We call them row stride and store stride. Because we didn't add any state, it's Linux ready, meaning that if you stay within the boundaries of the vector unit today, Linux already knows how to save, restore vector context. So we're not making any surprises for the Linux guys. If they know how to context save the vector state, these automatically work. So that was another very important goal of ours. And you read the last bullet before I talked, so int8, int16, fp16, and bfloat16, and all the accumulations are done internally at 32 bits. So as you do this over and over and over, you're not losing precision. So that's important also. What are the 3 new instructions? First one, vector load. If you're familiar with RISC-V vectors, normally it's called VLSE. There's a new letter in the middle, R for row, right? So it's a strided load with rows, right? And we've added 1 extra register which holds the number of elements per row and the row stride in bytes. If you want more details tomorrow, 3:30 in the demo theater, you'll get the full details. Same thing for the vector store, so they're just symmetric instructions, and then 1 instruction, actually 2 flavors of the same instruction, matrix multiply, A times B, resulting C, or A times B plus C, resulting in C, right? So 3 instructions. We did make the decision to make the registers being used by that instruction fixed. So you must put the data in the registers that you see there. There's no option to say, oh, can I put it in V9? No, you cannot put it in V9, right? It's got to be those registers. And we really sought out to make it easy, right? So I don't know how familiar you are with the representation. On the right side, there's a cube that represents matrix multiply, A, B, and C. If you're not familiar with it, don't worry. Think of it as A, B, and C, right? And so what's the loop? First three instructions in blue. What are they doing? They are loading the blue part, a submatrix of A, the blue part of the picture, into registers V8 and V9. Those of you that know the ISA will notice there's an M2, that's LMOL2, right, for loading two registers with one instruction. So the first three things are setting vector length, the new instruction that we invented, and an increased pointer. That's what these three instructions do. The next three instructions are loading a submatrix of B, the green data on the top of the picture. And we're loading actually 16 rows of B. Surprise, it matches exactly the 16 elements of A. No surprise, you guys are all smart. And we're loading them into 8 registers. So each register takes 2 rows. So if you can read the first 2 rows, say V0, V0, then V1, V1, that's not a typo. It's 16 rows in 8 registers. And then that's the next 3 instructions. And then that's it, one more instruction. You multiply green, excuse me, don't know my colors, blue times green, right? And you add it onto the purple that's in front. Where is purple being held? In registers V16 through V31. So you do that multiply and you accumulate into V16 through V31. That's it. And then you compare, am I done? And it happens so that A1, which is the pointer for the green data, happens to also tell you when you're done. So if I'm done, branch back. That's it. Literally 8 instructions. That's your matrix multiply algorithm, right? Now the key is, can we get it at full performance? Spoiler, yes, but that's about it. Of course, when you get to the end of the matrix, you have to store that purple data into memory. That's the thing that says store the C tile back to memory. Perfect, right? So that's okay. Or actually very interesting, you may actually run your activation function, ReLU, sigmoid, immediately without actually storing anything to data, even better. I'll insist on that point, because having the vector and the tensor unit together allows you to do that if your software is good enough, right? So I think we really achieved the easy part, and definitely we achieved the use the existing state, so we're pretty happy. Okay, that's our core. On the left side is the scalar part. If you're interested, talk to me later, but I'm not going to front end, issue queues, out of order, decache, our gazillion unit we all mentioned. Then in the middle there, we have the vector unit. We have the blue thing called vector registers. Those are the vector registers. And we have 8 vCores. We started calling these things vCores to see if people get the feeling of how a vector unit works compared to NVIDIA. Right, so as you know, if you've been following us, you can have 4 vCores, 8, 16, or 32, up to you, right? That's a different topic, that's not today's topic. But what's important is that directly connected to the vector registers, we got the tensor unit. So it's really reading from the vector register file, doing its thing, and writing back into the vector register file. So when that instruction finishes, your data is cleanly deposited into your into the vector register file. So if an interrupt arrives, it will be safe. So no problems, right? It is important to mention, I'm not going to spend time, but feel free to talk to me afterwards. Gazillion is our way to make many, many, many requests to memory, and it was already important for vectors. It's even more important for tensor, because this little monster there consumes data at an amazing rate. So you need to keep bringing data in to keep it running all the time. So the gazillion unit is a really key piece of the whole scheme, right? If you look inside the tensor unit, surprise, we call them T-cores. That wasn't too original, but again, the customer can select 4 T-cores, 8 T-cores, 16, or 32, so giving a range of performance is going to show up in the next slide in a second, right? Each T-core is actually basically 32 int8 MAC units, and those do int8 and FP16 and BF16, and as I repeated that, accumulations are done at 32 bits. So again, you can control the number of T-cores you get. So I mentioned that, but now that we have the picture, I'll say it again. The idea is you do the matrix multiplies on the tensor unit very, very fast. And if your software is clever, then before you even send the data out to memory, wasting precious memory bandwidth, you can run the activation function on that sub matrix block. I agree not all activation functions may be able to do that, but a large majority of them will be able to do it. So you actually save, on top of everything I said, you save yourself a bunch of stores that would have then been loads plus another set of stores. So it's really a great thing to have this integrated, right? Performance. Okay, we named these things T4 through T32. Fourth row, the number of tensor cores, as I was describing, 8 through 32, easy. What's important is to realize there's a dependency with VLAN. We made this decision to store our data in the vector register. So obviously, if you want more performance, you need bigger vector length. So that's not a free variable, unfortunately. So we do ask the customer, you want a T32, no problem. You have to make your vector length 4096 bits, right? Which is a good trade-off, because you were going to put that storage anyway in your chip no matter what, so you get 4096 bits of vector compute because you wanted tensor compute, so you as a double win, right? Another important thing, MLAN, that's the bus from the core to the outside world, right? We've started calling this MLAN. You've heard about DLAN, ELAN, VLAN, new name, MLAN. It's the bus required to sustain peak performance on the tensor unit. You can see we can do with 512 bits all the way to 216. If you want the T32, you'll need a bigger bus. So there's no way around it without more state, right? And the numbers are self-explanatory, I hope. So let's look at one. T32 gives you 2 Intel teraops per gigahertz. Again, we're an IP company. We don't sell silicon. We don't decide the gigahertz that the chip is going to run. You, hopefully, there's a customer in the room, you're going to decide the gigahertz that you want to run. So that's why we quote it at per gigahertz, right? So easy number. At 1 gigahertz, the T32 is going to give you 2 teraops. And I get this question, wow, I want more than 2 teraops. Well, put more cores, right? Very, very simple, right? Well, it's not simple to putting more cores, but anyway, having more cores is good for you. It's like having more apples a day is also good for you. You get more cores, you can run more stuff, you can run parallel stuff, you get more vector units. So that's our answer to, oh, what if I want to be outside the screen and have 8 teraops? Well, put more cores. Real results, right? Okay, what are we looking at? Horizontal axis, matrix size. These are square matrices. This is the T16, so the peak would be at 1 teraop. And what you're seeing on top is the teraops per gigahertz. So the best number you can get with the orange curve is hit 1. With the blue curve is hit 0.5, right? Because one is int8, the other one is BF16. And you can see we get there very, very fast. So we're above 80% somewhere 400 by 400, and we get to 90% somewhere in the 700 range, which is a really good number in these days of ChatGPT. The matrices are gigantic, so that's big matrices is not going to be the problem if you're running this, right? So very good results, very close to 90%, actually, above 95%. And then a real life example. We took YOLO. You've seen this slide before from me. We showed this slide in previous conferences with the vector unit. 2 novelties. First, we actually improved the vector unit, and we actually got this thing, YOLO, running on the vector unit with BF16. The previous time I showed this, it was with 32-bit precision. Now it's bfloat 16. And we already got to 5.6 frames per second. Fantastic from my last presentation. However, what's interesting here is that if you add tensors, you get to 33 frames per second. So basically, I know YOLO tiny is small, and I know it's not a big image, but fundamentally, you get 1 core with the tensor unit at 1 teraop, gets you YOLO at real time, give or take, obviously at a gigahertz, right? So give or take. So we're really, really happy, and you see the different layers of YOLO, what performance they get, and you can see certain convolutions are smaller. We get to really close to 100% for layers 6, 7, 9, and anyway, you guys can read that later. Actually, there was a question if you're going to get the slides. I don't know. It still says confidential because they made me send the slides a week in advance. It's like, God forbid. Anyway, conclusion. So, we've added three, if you want to count 4 custom instructions to the RISC-V Vector ISA. With those extra 4 instructions, you get a beautiful tensor unit. You as a customer can scale it up and down to your needs, so from 2 teraops down. It's really easy to program. Writing these codes is only a few hours, and I've shown you at 8 instruction loop doing the full matrix multiply, so it's really, really easy to use. And combining these with vectors is literally trivial. You just write your loop, and after that, you put your vector instruction. So there's absolutely nothing special to be done. No fencing, no atomics, no programming DMAs, all those ugly things you have to do with our competitors' NPUs, which many of you, for strange reason, enjoy doing it. But you shouldn't enjoy doing that, because programming DMAs is bug prone. Your software team is going to have trouble getting peak performance. Instead, this is really simple, right? So you use your normal tool set, no surprises, GCC, LLVM, all the standard stuff, and you get this running. And the performance, over 0.9 for matrix multiplication, and as an example, 33 frames per second for YOLO v3. So thank you very much. I don't know how much time I did, but any questions? No questions? Come on.
So as you mentioned, the monsters eat a lot of data. How do you simulate all this? Do you have Gen 5 models you give out?
No, this is all RTL running on the FPGA.
No, but on the FPGA. So
yes.
Basically your customer takes an FPGA and you work with them on the architecture on how to get the data in.
Right. I mean, we'll work with the customer to understand their memory hierarchy and to make sure that we size everything right. I mean, I did show MLEN, so there are constraints. If the customer says, no, I want that kind of performance with a 128-bit bus, we'll have to educate the customer saying, that's not possible, dear customer. You're always right, but not in this case, right? And we'll work with them to make sure that we cover the latency to their, whatever it is, L2, L3, DDR, you name it. Some people actually don't have DDR and only have a large bank of SRAMs. We'll work with them to calculate that.
Got it, thanks.
Do you have area and power estimates for one of those cores?
Under NDA, absolutely. No. Sorry.
So there's a box underneath the cache. Is that a prefetcher or?
A box underneath the cache. Oh, the gazillion unit. That's the thing that allows us to make many outstanding requests to memory, and that's the thing that guarantees that we'll stream enough data in for the vector and the tensor unit to get enough data to never stop. We provide an SDK, and we're now working, we're going to start working on ONNX runtime, but it's not, ONNX is not ready, the SDK is ready. Yeah, it's a very simple C, bindings for C and C++, so you can call our subroutines from whatever environment you enjoy. Right? Yes, not memory, correct. The tensor unit is not directly connected to memory. It does not have ugly DMAs inside. It doesn't do anything surprising to your memory. It gets all its data from the vector registers and puts back its results into the vector registers. That's what makes it Linux compliant. We have 4 reads, 2 writes. If you choose the CHI option, we support CHI natively, CHI.B and soon CHI.E. So yes, if this thing supports coherency natively, it's more expensive than the XI one.
You don't provide the OChip network IP.
No, but there are many vendors that do that. I mean, you got to buy a NOC from someone. More questions? Okay, thank you very much.